And I'll hand over to Ian Campbell to introduce our speaker this week. Thank you very much. Go ahead, Ian.
It's a great pleasure to be able to introduce Adam Kent this afternoon. Adam did his PhD at the ANU, and here's his thesis to prove it. It was completed in 1994. He came here from Armidale, where he was the top student in his year, first class honours from Armidale, and worked under my supervision, but largely with Ian McDougall, doing argon-argon dating in the Yilgarn of Western Australia. And the idea was to date the gold deposits there and to relate them to events in the formation of the Archean Yilgarn craton. And this is the first time this has been attempted. Ian McDougall was very skeptical as to whether it was a worthwhile exercise to do, but Adam succeeded in doing it and just an excellent PhD. He then went from here to Caltech, where he worked with Ed Stolper. I'm not sure whether he was there one or 2 years, but went from there to the Danish lithosphere project in Copenhagen, where he spent several years, I think about 10. And from there went to Oregon State University, where he is now. I visited the Danish lithosphere project just towards the end. These projects run for, I think it's 10 years, and then they're completely abandoned. And Adam had just left. He left a month or two before. And so people were still talking about Adam. And Adam was famous for what they called the Kent number. And the Kent number was the minimum number of geochemical points you need to write a first-class paper. And Adam apparently perfected that. You may think that that's a put down, but that's a mark, I think, of a good scientist who knows what he's doing. There's no point in getting 100 points that say the same thing that 10 points had already said. And Carl Terekian at Yale used to tell his students to get 3 points and a good idea. I'm sure he didn't mean 3 points, but there's no point in getting a lot of data, and Adam is very efficient in the way he goes about his science. To give you some idea of what he has accomplished, he's published well over 100 papers, and 2 of those papers are highly cited. There aren't too many of us who can claim 1 highly cited paper. Adam has 2. So I'm looking forward to this talk with great interest, and it's over to you, Adam.
Great, thanks, Ian. I'm going to stop sharing just a little bit, just so I can read the dedication to country, because as with you, I also live in a land that has an indigenous population. Oregon State University in Corvallis, Oregon is located within the traditional homelands of the Marys River or Apanefu Band of the Kalapuya. Following the Willamette Valley Treaty of 1855, Kalapuya people were forcibly removed to reservations in Western Oregon. Today, the living descendants of these people are part of the Confederated Tribe of Grand Ronde Community of Oregon and the Confederated Tribe of Siletz Indians. And now let me just get the sharing going again. And thanks for that introduction, Ian. And the education I had at ANU, even though I'm working on some quite different problems, I just had a fantastic general geochemical education, which has held me in great stead throughout my career. And I always hold that quite dear. I'm actually I have colleagues who also have PhDs from ANU, notably Bob Duncan, who many of you may also know. And I think we both realize how lucky we are to get such a great education. I can't remember the Kent number. I was worried it would have something to do with beer, so I'm happy it had to do with being very efficient in my delivery. And actually, I think this project, what I'm about to talk about tonight, is maybe a good example of that, because it uses everyone else's data and not mine. What I'd like to talk about is since I've moved to Oregon, I was just talking with Ian earlier about I'm lucky to be surrounded by active volcanoes, or volcanoes that have had Holocene activity. I can thoroughly recommend living on a subduction zone in terms of if you're a geologist interested in volcanic rocks. Of course, we haven't had a megathrust earthquake yet, so I might change my mind there, but still, it's a fantastic place. And I've become increasingly interested in volcanic processes in the almost 20 years I've lived here. Part of this is this project I'll talk about tonight, which is trying to understand more about what actually makes volcanoes erupt, and particularly using the insights you get from using the tools of petrology and combining with other things. The photo, for those of you that are interested, is Mount St. Helens, which is famous for eruption in 1980, but also erupted again in 2004 and 2008, not long after I arrived in Oregon, and that's a photo of the early phase of that eruption. The work I'm going to talk about is actually a collaboration with two of my long-term collaborators and two people I value a lot, both as friends and scientific collaborators. That's Carrie Cooper and Christy Till, shown there on the top left. Carrie on the left and Christy on the right. And they're shown quite near a large block of dacite, which is from the 1915 eruption of Mount Lassen, which was before Mount St. Helens in 1980 was the next most recent eruption, and one of the few historic eruptions of the Cascades. It erupted, amongst other things, this beautiful banded dacite, which is shown in that photo on the bottom. One thing about my computer, I'll point out that I will try and use the cursor if needed to point, but when I'm in this screen sharing mode, in display mode in PowerPoint, the cursor sometimes disappears, so I'll just try and work with that. Okay, so volcanic eruptions, I think we're all familiar with the fact that volcanoes can erupt. They can take magma from the interior of the earth and put it on the outside, and of course there's a large number of phenomena associated with that. It's something many people are interested in. It's often extremely spectacular. These are two photos that kind of show that, but I show them for other reasons. And the one on the right is Mount St. Helens, this time in 1980, where it had a very large eruption. It's quite a famous eruption. You know, I was in my first year at high school when I saw that, and many may remember there were several months of waiting for this eruption to happen, and then some very dramatic photos of this eruption and the accompanying blast and lahars. And so perhaps that had an influence on me and made me more prone to being interested in volcanology. The second one on the left there is Mount Pinatubo, which again had one of the largest eruptions of the last few decades in the early 1990s. This was when I was living in Canberra, and I can distinctly remember the amazing sunsets we got from the stratospheric injection of aerosol, which was also sufficient to lower global temperatures by measurable amounts for a few years. So these are two spectacular eruptions, but they're also ones that have some personal meaning for me. And of course, Mount St. Helens, I've actually been able to work on scientifically since I've lived in Oregon, and actually worked on Mount Pinatubo too. So a couple of facts before to sort of set the scene. One is this graphic here. If you talk to scientists from the USGS, from this, the observatory they have for the Cascade system, the Cascade Volcano Observatory is probably, they say, one of the most effective graphics the USGS has ever done. Really, it's just a sort of a map of all the volcanoes that are in the Cascades, and the little star that, if I have a cursor, there it is. That star there is basically where my hometown Corvallis is. The map of the volcanoes, you know, we're sort of going north to south here, parallel to the subduction zone. And the graphics on the right show how often each one of those has erupted over the late Holocene, the last 4,000 years, with the vertical red line being the last 200 years, sort of since recorded, since Europeans at least have started to make observations. And the take home from here, there's a lot we can go into. There's, you know, some volcanoes are more active than others, some are not. But the take home here is there are a lot of gaps there. And so particularly when I think this is relevant to nearly all volcanoes, but particularly when we talk about volcanoes that have to melt the crust or fractionate within the crust, frankly, they spend a lot of time not erupting. I think it's probably almost certain, perhaps not, but probably almost certain I'll go through my entire career, if I stay here at Oregon State and retire in 10 or 15 years, to have been extremely lucky to have witnessed one eruption, because there's been that one, there's been the eruption of Mount St. Helens in 1980 and Mount Lassen in 1915. So the rest of that time, all these volcanoes have not been erupting. So volcanoes spend a lot of time not erupting. And there's some words there, I won't read them out, but they come from a recent USGS document, which says that probably more eloquently than I just said it. Despite that, we know that the magmas that erupt out of these volcanoes sit around in the crust for a long period of time in some form. Now, they may not be in a form that lets them erupt. They may be too cold and crystal rich to do that, but nevertheless, they have that crustal residence. And if we look at geochronological systems that enable us to date these sort of ages, like zircon, uranium, lead, or uranium, thorium, or uranium series on crystals like plagioclase, the residence times of most crustal magmas are sort of in the thousands to hundreds of thousands of years range. And so the figure there shown on the right are some histograms of zircon ages, again from Mount St. Helens, from a paper by Lily Claiborne in geology in 2011. And again, it just shows the ages along the bottom there. That's the zircon, uranium, thorium model age. And, you know, the ages go, and some uranium lead ages, and they're several hundred thousands of years old. And this is not exceptional. Even if you look at a single crystal, which is that picture of the individual zircon in the center there, shows ages that range from 260,000 years to 73,000 years. So even a single crystal can record that long crustal residence time. So magmas don't erupt very often, but they're present in the crust. So the inference from that is it's actually probably not that easy to cause a volcano to erupt, and you probably need some unique circumstances to arise to make that happen. Another thing that leads us to the conclusion that it's actually not that easy to make most volcanoes erupt is that the magma that is present probably spends a lot of time of that storage I just talked about in a state which we could describe as uneruptible, at least in terms of viscosity. I won't dwell too much on this this figure here. It's from a paper that I published with Carrie Cooper some years ago. I actually talked about this. The last talk I gave at ANU, which I just noted from earlier, was in 2016, and another one was in 2010. So I guess I give one about every 5 years, which is great. Basically, the figure on the left is just a kind of a literature comparison of uranium, thorium, or radium thorium ages for volcanic rocks. That's the solid symbols. The lines are ages based on diffusion. Now, diffusion is a thermally driven process. Ages based on uranium, thorium, or radium, thorium, and not. They're just, once you fractionate the parent daughter, the clock starts ticking with radiometric ages. And so the difference between those is ascribed to the fact that these magmas spend most of their time quite cold, and diffusion is not really happening. If on the right there is another picture of a zircon, and you can even see this happening in individual zircons in a paper again with by Ali Rubin, who was one of Carrie's graduate students a few years ago. We're able to show that if you look at the distribution of an element like lithium, which diffuses pretty quickly, in the zircon, you can find areas of lithium enrichment, which you can then model by diffusion and sort of place constraints that this particular crystal hasn't spent more than a decade or so significantly above 750 degrees, which is quite cold, and probably below about 750 degrees is the temperature at which a magma would be rheologically locked up. So even though we're dealing with a 50,000-year-old crystal, it spent relatively small amounts of its lifetime in conditions where it could erupt. And that's just probably one of the things that makes volcanoes hard to erupt, is that most magmas, most of the time, are probably not eruptible. So we need to do something special. So then, you know, it falls from that understanding what I call initiation, which is basically the process of going from this stably stored crustal state, uneruptible or not, to actually erupting, is a key process. And I think it's interesting to note that this is something that the volcanological research community has more work to do on. I think it's been a bit of a blind spot, and I think that's understandable. There's lots of interesting things related to volcanoes to study, but one example of this blind spot is the Encyclopedia of Volcanoes, which I show that this is the cover from the second edition here. This is sort of a manifesto of all things volcano. It has 70 chapters and over 1,500 pages, something like that, of information about volcanoes. It doesn't have a chapter on initiation, and very few chapters actually delve into this process of initiation. So I think there's some scope to do more work here. But before I get too much into it, I have to get a little bit into definitions, and I'm sorry if this is too much detail for those of you that don't think about volcanoes every day. But one of the problems, and I think this is probably true in many fields of science, is that many people talk about similar processes with different names and different processes with similar names in volcanology. So there's some nomenclature to be sorted out. As I said before, for me, a definition of eruption initiation is just something where you take magma that is within the crust and stable. And by that, I mean, you know, all geophysical signals would be at baseline and no indication of magma moving up. So changing that to the point where magma starts to move upwards through the crust and eventually to erupt. And that's a little different to this idea of eruption trigger. Often initiation and trigger can be used as synonyms, but trigger is a more generic term. and can be used for a range of things like collapse of a lava dome, collapse of a lava column. So I'll be using initiation sort of in this context. You can understand this difference. These are two photos of Mount St. Helens taken a few weeks apart in 1980. The top photo shows this bulge, the famous Mount St. Helens bulge, which was occurring on the top of the north side of the volcano. This is basically caused by what's called a cryptodome. It's a very shallow intrusion of magma, like something like you might think of like a laccolith or something like that, that's intruded so shallowly into the volcano, it's noticeably deforming the volcano. So that's hot magma. It's under some confining pressure there. Eventually, that magma, the top of that mountain became gravitationally unstable and collapsed in a major landslide. And that was actually the trigger for the eruption. It was a release of confining pressure throughout the system that allowed both the magma in the cryptodome to explode outwards and laterally to the famous lateral blast, but also magma stored deeply suddenly was relieved of its confining pressure and moved upwards very rapidly to form a Plinian column and a very large eruption. That was a trigger, but that is not what initiated that eruption. What initiated that eruption occurred several months before, where magma deeper in the crust moved upwards into the edifice of that volcano. So I'll be talking about the latter process, not that the triggering process of various types of volcanic phenomena is not uninteresting also. So what actually does it make what does it take to make a volcano erupt? And I think we have a reasonable idea of this. People have certainly considered this. At its very simplest, we have a package of magma. Let's assume that magma is sufficiently rheologically mobile to move within the crust that exceeds its confining pressure. Some sort of critical overpressure or tensile stress is reached that allows it to fracture the rock above it, and then magma to propagate up a dike or a magma-filled fracture to the surface. This is basically shown in that cartoon up on there on the left, which is from a paper by De Gruyter and Huber from 2014 in EPSL. That sort of laid this out. It was these two are both numerical models, so it was a numerical modeling paper, but it sort of lays out this idea. Of course, we don't know what it actually is that causes that overpressuring to happen, and that can probably occur in a number of different ways. And the figure on the right goes into a little more detail about that. It's basically a comparison of two dimensionless parameters. Let's see if I have a cursor. I can't have a cursor. So the bottom is sort of a parameter related to how quickly you're adding magma to that system. That would basically be this arrow here. You're adding magma in, probably from below. If you're adding it rapidly, you're adding heat to the system quite rapidly, and you're adding mass and increasing the volume of that system. If you're adding it slowly, you're cooling more rapidly because the system is allowing to cool by conduction, and you're crystallizing more rapidly. So that's one dimensionless parameter. The other just relates to the rheology of the crust, going from viscous to elastic. So more elastic behavior to more viscous behavior. And on this figure, Chris and Wim, the two authors, were able to sort of map out 4 regimes related to possibly different ways of triggering an eruption. The first is where you're crystallizing quite rapidly, but the crust is elastic. When you crystallize rapidly, you're probably saturating the residual melt in a vapor, and that results in once you do that, it results in a rapid increase in volume because you're producing essentially bubbles within the system, and that lets an eruption be triggered by second boiling, increasing the overpressure by what's called second boiling, which is just an increase in vapor pressure. In contrast, if you have an elastic crust but you're adding material really rapidly, you can just increase this overpressure by basically trying to stick too much magma in somewhere that it can't hold it, and it ends up generating an overpressure. Conversely, if you have rapid injection but a crust that's behaving much more viscously, you might be able to trigger a magma by buoyancy forces. And then there's this kind of fourth quadrant, not quite a quadrant, where no eruptions. So we have some sort of framework. The difficulty we have is taking the eruptions we see and fitting them into that framework, and then iterating to both improve the framework and improve our knowledge of what is initiating eruptions. In addition, more recently, there's a concept we also have to fit this within, and that if I go back one, this is a simple cartoon. I think no one would argue with the fact we just need a simple cartoon here to understand that. But magma chambers don't look like that. In fact, I don't really like to even use the term magma chamber because it sort of implies a large body full of magma. I tend to use magma reservoir, although my friend George Bergans then says he just thinks about people, you know, water skiing at some dam or something. So I don't know what the right term to use is. But the thing, we're dealing with a more complicated system than just a balloon inside the crust that we're inflating and deflating. And that comes down to a more recent idea, which is this thing called actually it's not that recent idea, but its time is coming. This thing called a transcrustal magma system. That is that volcanic systems are underlain by material being fed in, probably in almost all cases from the mantle, adding heat and material. And between that and the volcano at the surface is a very complex system. So it's complex in terms of geometry, in terms of its thermal structure. There can be can be rapid changes in temperature with respect to geometry. Composition and crystallinity likewise could vary quite substantially, again, in part reflecting the thermal complexity. We could also have variations in gas and volatile abundance, variations in rheology, again, tied to thermal structure. And of course, this is a system that's not static, it's also changing all the time. And the cartoon on the right, sorry, I should have pointed out, is from a paper by Marie Edmonds, and it's strictly for Soufriere Hills, which is the volcano on the island of Montserrat that erupted in the 1990s and early 2000s. But it's more general. This more general cartoon. It just points out that there are probably a number of different bodies, perhaps sill-like in geometry, of different compositions, and again pointing out the complexity. So a range of complex processes occurring in the system. It's basically fed from below. It advex heat out the top via eruptions of magma. So the things that initiate eruptions are happening within the system. So to understand this problem properly, we really understand what's happening in the initiation of in this transcrustal magma system itself. So this is in many ways this was a big advance. One way is it reinforces the importance of understanding plutonic systems. So on the bottom left, I have sorry, I'm just checking the time. I have a photo of a bald rock, which is in Tenterfield, just a few hours drive from where I grew up. And Eastern Australia is full of batholiths, the New England origin, where I saw a lot when I was an undergraduate, the Lachlan origin. And these plutonic systems were part of this transcrustal magma system. So in order to understand volcanic eruptions, we also need to understand sort of their batholithic roots. So I want to talk now a little bit about why I think petrology, the study of rocks themselves, is a way forward to this. And I'm going to do it against this backdrop. Again, there's a bit of a theme here of Mount St. Helens running through. This is a time lapse of the dome intrusion event. This started early in 2005, this time lapse video. And you can see that this was a very interesting dome intrusion event. It occurs as a series of whalebacks. So you get these smooth whalebacks that occur, and then eventually they get too big and become gravitationally unstable. It was a very interesting dome intrusion event because the material that is coming out of the volcano is essentially a solid. And in fact, it's so solid that the smooth parts of those whalebacks, you see, another one will grow in a little bit. There was a succession of them that grew over a few years. The smooth part is actually more or less a fault gouge. It's a cataclysite type rock. So that rock is rheologically a solid, and along its margins, where it's extruding out of a conduit out of the crust, is being deformed just like we would expect any other faulted rock to do. But the other thing this reinforces is that the great thing about petrology, actually the great thing about volcanoes, is that they bring samples to us. So the rock that is being brought out of the earth at the moment has experienced some of the physical and the chemical conditions that led to this volcano to erode and erupt. So we actually have material that has experienced these conditions. The other thing is that the seismograph that's shown here on the bottom left is a seismograph. I don't think it's the entire period of time that movie showed, but it shows that the extrusion of this dome was characterized by this interesting seismic behavior, which are characterized as drumbeat earthquakes. These are earthquakes of very similar seismic forms. Sorry, I'm not a seismologist. I probably could have used a better word to describe that. Very similar waveforms and occurring at pretty predictable intervals. Like drum beats. And in fact, you could take the seismogram and speed it up and you can listen to it and it sounds sort of like drumming. This was basically showing stick slip behavior. So the dome is so rheologically solid, it would stick for a while, then the force from below would exceed the critical pressure and it would move forward a little bit, and every time you get a small earthquake. So the interesting thing about this is not only do you get the rocks, but you also get to link the behavior of how those rocks are coming out by looking at the geophysical signals. And this is a theme of modern volcanology. You know, if you look at a modern eruption, you will have geophysical signals like earthquakes, like deformation signals, GPS and tilt. You'll also have gas measurements. You'll have lots of measurements of these rocks, and you'll also have the rocks themselves to look at. And this can be really useful. So I'll be talking a little bit about timescales, and I'll explain a little bit more. But when you look at crystals from magmas like these, you can often generate timescales since something happened to that crystal. In this case, the growth of a rim. That's what the figure on the upper right shows. It shows magnesium ion zoning in orthopyroxenes from erupted material from 1980 St. Helens. And those pronounced rims, changes in grayscale around the edges of all crystals, you can use those, the boundaries of those, to sort of estimate the time since they formed. If you know a temperature and you're just basically comparing an observed distribution of some given element against a inferred initial distribution, you count that, you measure the diffusive relaxation. The interesting thing here is if we go to the figure on the right, and if I have a cursor, this will be interesting. Okay, so this is sort of a histogram or a PDF of a number of some timescales generated by looking at these diffusion gradients. And there are a couple of noticeable peaks which sort of broadly line up with seismic swarms extending to depth. So it's clear that we can use the, and exactly what this is, still not completely sure, but probably relates to relatively rapid movements of magma from deeper in the system up into the shallow magmatic system. And that seems to be recorded by the crystals as well. So an increasing theme of understanding the petrology of eruptions in young eruptions, where we also have a geophysical monitoring record, is to try and relate what we see in the rocks to what we see in monitoring. And this is very important. And it's probably one of the justifications for this, the approach I'm talking about tonight, or for me tonight, for you this afternoon, is that, you know, in many cases in the past, monitoring of volcanoes where you have a geophysical record of some type, earthquakes, deformation, some other things, has been largely dominated by pattern recognition. Say, okay, I saw this last time this volcano erupted, we saw this sort of seismogram. So if we see it again, we might infer the same thing is happening, and that's fine. It's been very useful, but there's a widespread recognition in the community that we also need to move more towards a modeling or a forecasting system that we're understanding the physical and chemical changes that are happening within the magmatic system and the surrounding rocks that are producing those geophysical signals. And so work like this that takes actually the rocks, looks at them, sees what has happened, and then tries and relate that to geophysical signals is becoming very important. So the point I want to make, and one of the take homes for this talk, is that within this whole theme of understanding eruption initiation, sort of a petrological approach, a study of the rocks themselves, has a sort of an underutilized but a really rich record that we can take advantage of to a greater extent than we are at the moment. And there's a number of reasons for that. You know, one thing is that the last high temperature geochemical process that typically happened to a volcanic rock is the thing associated with eruption initiation. Now, that's not completely true. There are processes that occur in conduits and in domes, but at least the eruption initiation occurs very late. Now, volcanoes and magmas in general are like many other geologic systems in that each succeeding event can act to sort of obscure the evidence of what happened before it. So the fact that we're looking at one of the most recent events gives us a much cleaner record than if we're trying to peer back into the very origin of that magma and trying to work out what happened a long time ago. Here we're trying to work out what happened just, you know, in many cases, just days, weeks, or months ago. And so things like looking at what happens at the edges of crystals becomes very important. And this little montage here of does sort of an example of the type of evidence we have. We can look at the edges of crystals. We can look at things like melt inclusions and fluid inclusions that occur within crystals, but also maybe some sort of have some distribution that's important. We can step out to bigger, and also we could look at things like the breakdown rims on amphibole crystals, although often they're related more to magma ascent. We can step out and look at the populations of crystals that might occur at a thin section scale But then we can also look at features like mafic inclusions or banded pummices that are at the hand specimen or outcrop scale. And then we can also step back and look at the field scale and look at things like changes in crystallinity or changes in composition in zoned eruptions. So there's a lot of tools we have, and there's a relatively well-preserved record. One of the other big advantages about petrology is that it lets us sort of do forensic investigations. I actually don't like to use the word forensic with respect to this type of thing, but I do a lot. So there you go. What I mean is, you know, we can, like I showed you before, we could take Mount St. Helens and look at crystals that came out in 1980 and compare it to the geophysical record. That's great. We have both the geophysical record and we have the rocks. We can't take that geophysical record back into geologic history because no one was there to record the seismic signals. However, we can look at the rocks. So petrology gives us a way to tie the geological history of a volcanic system with the higher fidelity modern record we have from putting instruments on it. As I said before, we're also getting information, more and more information about timescales, and I'll talk about that a little bit more because it's very important. We have tools now which we can actually evaluate volcanic events on important timescales like days, weeks, months. So some important questions we can then ask, you know, and I'll address some of these in the subsequent talk, but perhaps not all. You know, what are the mechanisms that initiate volcanic eruptions and how are these recorded through looking at the rocks themselves? Can we identify volcanoes that are consistently erupt by specific eruption initiation mechanisms? You know, if someone says there's a volcano, we need to understand its hazards, one of the key things you would do is you would go and map that volcano. You would look at the eruption styles that have occurred in the past. You know, are they explosive? Are they lava flows? And you'd look at the chronology. Well, I also say, why could we not also characterize a volcano in much the same way, but try and understand what has caused each of those eruptions that are preserved in the geologic record? And then, of course, I already raised this. I'll do it quickly. You know, if we understand more from petrology about what physical and chemical processes are occurring during eruption initiation to actually make that initiation happen, can we fine tune our volcano monitoring? Can we then start to recognize distinct physical and chemical processes occurring in the subsurface from the volcano monitoring record? And if we know that, will that give us then some predictive power? You know, if we say, okay, well, this looks like this volcano is clearly, you know, a volcano that we have signals above baseline, perhaps we can then infer what the processes are that are occurring, eruption initiation mechanisms. Does that then give us some predictive power in terms of, I think my headphones just ran out. All right, nothing like, hey, Louis, can you just let me know if you can hear me?
Yeah, we can hear you just fine, actually. So that's fine.
Louis, can you let me know if you can hear me?
Yeah, we can hear you. We can hear you better than you can hear us, I think.
Just gonna. Sorry, Louis, just say it again. Can you hear me?
Yeah, we can hear you.
No,
You're coming through loud and clear.
Can't hear me.
So yes.
But you can hear me?
Yeah.
Okay, all right, I'll keep talking. I'm going to keep the window with you in it. So if I get the thumbs down from you, I'll know that I have to start doing it by mime. And so I just say, is there predictive power? Do we get some knowledge in terms of, you know, prediction is sort of the wrong word. It's like earthquakes. It's the wrong word to use for volcanic eruptions. It's forecasting is a more appropriate word. But do we get something if we know about initiation mechanisms? So let me. All right, so the way I've done this, I've used some of my own studies, but I've also, with my collaborators, we're basing a lot of this on a larger literature review. And what basically, since this is sort of early days in this approach, we've sort of tried to mine what the literature tells us. And so I'll be presenting the results in a little bit of a larger literature study that lets us sort of answer some of those questions I just talked about. And basically, this is a summary of of where we are. Okay, so in terms of petrology, we can recognize a number of different eruption initiation mechanisms, and of our compilation, almost more than 90%, actually, sorry, less than 90%, just less than 90% relate to intrusion of new magma. So this makes sense to, I think this makes sense to me, because I said it looks like we need some exceptional event often to happen to make a volcano erupt. And what could be more exceptional than adding other magma from below, to a system? So that certainly seems one good way to perturb a magma. Exactly how that works, we don't know. We see some volcanoes, for instance, that we see evidence of repeated magma injection that does not cause an eruption. We see some volcanoes that look like they're very sensitive, and so they're kind of ready to go, and any injection of magma causes an eruption. So there's clearly something to be understood there. But it does look like magma injection is a very important part. And this is probably, it's interesting. It's probably no news to some people who've realized this for some time. But there are different ways to do it. You can have a silicic magma in the shallow crust, which is hit by a mafic magma. And we can have and essentially we have a continuum from that situation where there is a big compositional contrast between the two magmas that are interacting, to one where there's almost no compositional contrast and perhaps just a mild thermal contrast. And I've pulled those out differently. I call one recharge. I call one rejuvenation. That's just to sort of clean up nomenclature. But the reason I think there is good justification for pulling this out, because the physics and the chemistry of what actually is happening to exceed overpressure in those situations could be quite different. And I'll show a little bit of evidence there, because there's a nice ANU history link on that. And so we have these different mechanisms. You can have mafic recharge where mafic magmas intrude a silicic magma chamber. You can have mafic rejuvenation where mafic magmas intrude a mafic magma chamber, and then you have silicic rejuvenation where silicic magma chambers intrude a silicic magma chamber. And we see evidence for all those. I'm going to review them briefly. I'll probably go quite quickly because I'm not quite sure when I'm meant to finish, but it's probably, I don't want to be here for too long. And then there's a final mechanism, the only one that you can see petrologic evidence for, that is not related to introduction of new magma, and it's actually a bit of a grab bag, but it's accumulation of vapor or second boiling. It's this thing where you increase vapor pressure either through crystallization or perhaps by streaming of vapor from below in a system. By increasing vapor pressure, you exceed overpressure. So they're all in these sort of yellowy, orangey boxes are the ones that you see distinct petrologic evidence for. But there are another family of eruption initiation mechanisms that perhaps you don't see petrologic evidence for. And it's worth remembering that, when you have a hammer, every tool looks like a nail. So here we're using petrology. We'll see systems that leave distinct petrological signatures. We might not see systems or mechanisms that don't do that. And so things like buildup of buoyancy, failure of a roof, the effect of far-field tectonics like a very large earthquake, all those might have either no petrological signature or much more subtle signature. And so we need to remember that there's sort of an observer bias, potential observer bias at least here. I was going to go through some of this, what evidence like this looks like for petrology, and I will. The mauve boxes in all cases are just a list of evidence. I won't go through this. I'll just describe the examples that I show in the figures. I think this is the case of mafic recharge when you're adding a mafic magma to an intermediate or revolved reservoir, or perhaps a mush, which I use to denote something that has that is very crystal rich. So it's not mobile like a magma, but essentially it's a magma that has got too much crystals in it by cooling to be mobile. And you can see evidence for this. You can see the main evidence you see is interaction of these two mafic and felsic composition. So an example here shown from Mount Hood from a paper I think the first talk I gave at ANU in 2010 after I was in Oregon was on this. But this is a plagioclase crystal, and the red line shows a line along which we've analyzed every point. The grayscale here reflects the calcium to sodium ratio, and the lighter grayscale is calcium rich, the darker is sodium. And so this is the composition of that crystal in terms of anorthite proportion. So high numbers are calcium rich, lower numbers are sodium rich. And you see there's this sort of interesting variations. That's great. If you then look at the element iron, it's sort of uniformly low. And right at the end, there's a zone where it kicks up. So this is the indication that an iron-rich magma, so a mafic magma, has intruded something that had low iron, so a silicic magma. this is really common at Mount Hood. In fact, every sample I overlook shows this signature. So we all see all plagioclase crystals, which are what the photos here all show, have these zones. They're higher in anorthite, but they also have higher iron. So this is an indication of an arrival of a mafic magma that into a silicic chamber. You know, and it also, you know, nicely shows that there's, it's not saying that other complicated things don't happen. The interior of these crystals also often show a very complicated textures and by inference a complicated history. But we're really, you know, the nice preservation of those interior events is harder, or try to place them in context is harder. When we're looking at the rim of a crystal, it's actually quite clear this is the last thing that happened to this magma before it erupted. Again, other types of crystals show the same. This is orthopyroxene. Again, the grayscale shading relates to chemistry. In this case, light colors are iron rich, darker colors are magnesium rich. So in this case, this is what we call a reversely zone. This is addition of a more magnesium rich magma, which would be a mafic magma. And you see sort of both types of zoning going from light to dark and dark to light. So again, there's very good evidence. This is what good petrologic evidence for mafic recharge looks like. Those crystal margins also are great places to get some constraints on timing from diffusion, because the initial geometry of that crystal margin probably approximates a step, which is a very simple diffusion. You can model that analytically using diffusion modeling. There are analytical solutions for this geometry. And by doing this, in this case, this is the distribution of magnesium across two crystal rims. You can show if you have to infer a temperature, but you can say, okay, so this rim formed and then this rock cooled in 10 days. This is actually quite a useful timescale. Even if you're an emergency manager, for instance, if someone says, okay, something happens at Mount Hood, how much time do you need between when we detect something through changes in gas or changes in earthquakes when it comes out of the ground? And if your answer is 7 days compared to 20 years, then the response will be quite different. So this timescale is actually quite useful, and petrology in this case is, you know, contributing really quite useful information that has a very practical use in terms of understanding the hazards and the management of a future eruption. I also wanted to say, you know, we understand something about the physics of this, and a lot of this comes from work that was done by Stuart Turner and his co-workers. It's kind of cool to call Sir Steve Sparks, who's now a Sir, just to refer to him as a co-worker. But of course, Hubert Huppert and Steve Sparks and Stuart Turner are all understanding the implications of what happens in volcanic magma chambers when you, in this case, the word was replenished, when you add a hotter, more dense magma underneath a less dense, more silicic magma. A lot of this stems from observations that Steve actually made at Askja in Iceland, which is one of the first, from an eruption in the 70s, which is one of the first sort of realizations that addition of magma to a magma chamber is important. And then there are other ways. You can also look at systems where it looks like the magma that arrived in the shallow crust was not mafic, it was silicic. And so you'd see different types of minerals that are present. You see different types of zoning patterns, and you can infer things like the temperature difference was much less between the two magmas. In that case, we're dealing with two magmas of broadly similar composition. That means the phase stability remains broadly the same, but it also means the physics could be quite different. So being able to recognize this purely on petrological grounds is quite useful. I'm skipping through this because I don't want to talk too long. The equivalent of this in the mafic world is something that happens probably in almost all large shield volcanoes, like on Hawaii, Kilauea, Mount Etna, Reunion, and Piton de la Fournaise in Reunion. And that's when you have a mafic magma that is stored in an upper crustal chamber. Perhaps it's actually a crystal-rich mush formed by gravitational separation, which is then intruded by another mafic magma, and then that results in eruption. Some examples: there is an olivine crystal, a false color crystal of an olivine crystal shown here. It has a magnesium-rich rim. So magnesium is in a relatively more mafic magma that intrudes. It leaves a magnesium-rich rim. Again, a great situation for doing diffusion modeling, and there is a ton of information now on the timescales associated with these types of eruptions. But you can also see other evidence. And so this is actually from a paper by my student, Richard Bradshaw, that was published a few years ago. This is a plastically deformed, a strained olivine crystal, and nearly all these large basaltic eruptions have some smaller population of olivine that shows strain. the interpretation of this is these are plastically strained crystals that form in olivine-rich cumulates, probably formed by gravitational separation that deform sort of under their own weight or under the weight of the crust in the magmatic system above them. And then they get remobilized by addition of new basaltic magma. So that's sort of like a evidence of the mush that's being excavated by this eruption. And finally, the example I gave, which is much more rare in finding petrologic evidence for this, but it happens, and that's evidence for initiation of eruption by volatile accumulation. And I've already shown several other photos of Mount St. Helens, either in 1980 and 2004, and we actually have a paper from 2007 in geology that argued that this was the mechanism in 2004 that initiated eruption. The basis for this was seeing an increase in an element, lithium, which is vapor transported, what I call vapophile, with apologies to Goldschmidt. I don't think he used that, but atmophile doesn't really work in this case, so we call it vapophile. This is an element that is carried by an exhaled vapor from deeper in the systems. It builds up in the upper part of a magma chamber, sort of in an apice, like a classic ore geology thing, if you like. Some of that lithium diffuses back into plagioclase, which are what I'm showing of measurements here, which then erupts. And what we have here is a time series through this eruption. Yeah, this is eruption of the same dome, but the USGS were able to sample this literally by hanging a bucket, a big iron bucket off a helicopter and dragging it up the side of the dome. So we got this fantastic time series, this eruption, and it showed that it had this unusual early phase that is enriched in elements that you would expect to find in a vapor. So the inference from this is that this was a vapor accumulated at the top of this volcano. There's some other evidence for that, at the top of a magma chamber, eventually exceeded the vapor pressure, built up and exceeded the confining pressure and helped magma start to move upwards. Just another little bit of evidence for that. This is a photo quite similar to the photo on the title of this slide. And that's from the very early days of this eruption. This is actually a dome from the 1980s eruption, but we're starting to see obviously steam and ash streaming from fumaroles. Adjacent to this, there'd been a couple of small explosions at this point. Originally, they were thought to be phreatic, which is just interaction of magma and heat, but doesn't need to include new magma. But we could identify a high lithium fraction in that, which is juvenile, which means that it's actually new magma. And so this was sort of the first indication that new magma was coming to the surface. And so this actually could be quite a useful tool for recognizing juvenile magma in future eruptions, or recognizing that magma is actually playing a role. For instance, the eruption of White Island that occurred just last December and tragically resulted in loss of life. An interesting thing to know in that is whether there is actually new magma involved or whether the heat that's causing that steam explosion is just residual heat from the magmatic system. And of course, I've gone through some petrological information, and I'll be the first to tell you that petrology needs to get the house in order too here. I've said that this is a bit of a blind spot for volcanology, but part of that comes from petrologists needing to, and it's the way science works, is having difference of opinions and trying to refine the actual petrological interpretations that we use. This is just an example from the eruption of Calbuco, which is in Chile, which happened in 2015. Another interesting eruption because it's a VEI4, which that's the volcanic explosivity index. It's kind of like an earthquake magnitude scale for volcanoes. A VEI4 is pretty big. Mount St. Helens in 1980 was VEI4. It's up to about a cubic kilometer of rock, which is quite significant. So, but this one happened with about 3 hours of warning from the remote observations being above background. So there was an earthquake started, and 3 hours later you had a very large Planaean VI4 eruption. And if you look at these two papers, there's subsequently a third one that's come out, but they basically ascribe completely different mechanisms to the initiation of this eruption. So even presented with broadly the similar evidence, it's possible to have different interpretations. So now I just want to take you through this literature compilation a little bit in the last bit of the talk I have. Let me see, yes, I probably should end up, if Louis, if you need me to end, just sort of come on camera and then give me a stern look. I've probably got about 5 minutes to go. I want to look at I talked about this literature compilation, and one thing we did was try and find volcanoes that we could identify from petrology being initiated by different eruption mechanisms, but then record other things like the eruption style, the composition that's erupted, the time scale, so using diffusion and other kinetic processes to estimate the timing of that initiation process and the volume. I'll skip through the details, but I will point out that you know, you can do some good statistics on this, but you need to use a categorical approach, because things like erupted volume and timescale are numbers with high amount of uncertainty. A typical study might say, we think that this initiation happened within years to centuries. And so dealing with years to centuries is basically, it is a numerical term, but it's so uncertain, and it's not quite clear where the weighting of uncertainty would be if you took an average value, that it's easy to just use a categorical approach. And so this is a table that you use to divide stuff up categorically. And so volume, for instance, you can place as an eruption less than a cubic kilometer, 1 to 10, such forth. And then to also simplify this statistical approach, we just took what's called a dichotomized approach. This is borrowed from the social sciences, where you basically, you give yourself two categories. You know, it's basically have a dichotomy. And that makes the statistical approach a little easier. And so you can see all the factors I talked about: volume, time scale, eruption type. This is much simplified, and the reason it's simplified is we don't have that much data. So if you start to make too many categories, you lower your overall statistical power, because your categories have too few data. Already we had that problem. So we took the simplest possible path. These histograms just show that if you look at different eruption initiation mechanisms, here are our four: felsic rejuvenation, mafic rejuvenation, mafic recharge, and volatile accumulation. And the proportions in this case of volume, so the colors reflect the percentage of total per category of each of those. There are distinct differences. I won't get hugely into what those differences are, but there are distinct differences. So what that says, we might expect that eruptions initiated by volatile accumulation, that's not a great example because we have so few of them, so let's say felsic rejuvenation, they have a different sort of spectrum of volumes than you would expect from mafic rejuvenation. So if you know an eruption is going to happen by one of these mechanisms, perhaps that gives you a little bit of predictive power in terms of understanding what the volume might be, which is very important for an eruption, because less than a cubic kilometer is much, much different than greater than 100 kilometers cubed. Eruption style is the same. I'll gloss over that quickly. And then if we looked at erupted composition, which is not the greatest thing to look at, because honestly, if you're intruding a mafic magma with a mafic recharge magma, you're going to end up with a mafic composition. So there are distinct differences in composition, but it's perhaps not too surprising. But there are also differences in time scale. And so we also want to know if an eruption is initiated by mafic recharge, for instance, are the time scales going to be distinctly different than it's initiated by felsic rejuvenation? So do our mechanisms relate to different timescales? And I already said that this timescale is one of the most important things, because it directly feeds into sort of how you would manage a crisis at a volcano that would erupt in these different ways. So it's quite interesting to see that they look like there are differences. And then we took a little further, because we wanted just not to say, oh, gee whiz, they look like there are differences. We wanted to know if there was statistical support for that. And so again, borrowing from the social science literature, we use some tools for comparing categorical variable distributions. You know, you can do this with a chi-square test, but when you get to low numbers, the chi-square test sort of becomes less useful. And so we use this thing called the Fisher exact test. And I will say, you know, I grew up on a steady diet of BBC comedies and TV shows. I've never met anything more English than the Fisher exact test. The Fisher exact test was determined actually by a really smart vicar in the 1930s. But it was specifically derived because one of the ladies who the vicar was talking to said she could tell the difference between a cup of tea if the milk was put in before or after the tea into the cup. So he then worked out this hypergeometric distribution. I actually don't know how he calculated it without computational support in the 1930s, but he developed a really useful statistical technique for being able to tell the differences between categorical distributions. What it does is basically you say, okay, there is a null hypothesis. The null hypothesis is that there is no difference. So in this case, I've summarized in what's called a contingency table for the different eruption mechanisms. And in this case, comparing explosive to extrusive, we see, you know, 12 explosive felsic rejuvenation eruptions, 5 extrusive. And for each of the different categories, we have this breakdown. What the Fisher exact test lets us determine is the probability of getting this distribution if the null hypothesis that no difference is correct. So it calculates a p-value. If the p-value is low, the chance of your null hypothesis being correct is low. If the p-value is high, you can't distinguish your results from this null hypothesis that no difference exists. And this is an example of that. So for instance, what we have here, this distribution here has an exceedingly low probability of coming to be if the null hypothesis is correct. And you can sort of see that, there's a big difference in proportions, 12 to 5 versus 2 to 20. If we compare all these categories and in this type, we get low p-values. The interpretation of the p-value, in previous times, you'd say, okay, so less than 0.05, right, we're calling that statistically significant. The interpretation of that has sort of moved on, become a little more nuanced. But what we're looking at is if there are low p-values, then this sort of gives us an indication that there are distinct differences in these categories with respect to eruption initiation mechanisms. And this is a reason to explore further, to make some new hypotheses and move forward. I'll skip these slides because they are more about this, and they don't really show more. They just sort of show that we do believe there is some sort of predictive power in knowing the eruption initiation mechanism in terms of understanding the erupted volume, the eruption style, or the eruption timescale. This is a cartoon that my colleague and co-author Christy Till put together that sort of summarizes that. It sort of fits it into a framework of magmatic systems that have shorter to longer run-up times, that have eruption initiation timescales that are short to long, and as you go from mafic rejuvenation to mafic recharge, volatile accumulation, felsic recharge, these things sort of consistently change. Now, this ordering here in some cases is supported by what appear to be statistically significant differences. In some cases, it's more just an observation of changes in proportion, but it does tell us that there is some interesting stuff here. And if you're interested, what I've talked about has been written up. It's actually as a preprint on the Earth Archive server now, if you're interested in having a look at this in more detail. So where do we go from here? Well, I think I'm arguing, well, I don't think, I know, I'm arguing for it's time to put an increased emphasis on eruption initiation processes. And I think petrology can really help. Yes, we need more data, we need more accurate data, but we also just need more data because we need more statistical power. We need to be able to break down into finer categories and still make statistical tests. So there's more to be done, but I think there's something there. I also want to point out that now is a great time to be working in volcanoes. There's a number of initiatives that are going on in the US, which I'm familiar with. I was just this past 2 days in this thing called a Converse workshop where we did a tabletop simulation of eruption of a continental US volcano and what the science response would be and how to organize the science response, which was fantastic. There is the NSF has funded sort of an exploratory part of this thing called the SC4D initiative, which is trying to understand subduction zone hazards. So it includes earthquakes and landslides and stuff like that in 4D. And finally, if you're interested in this, the SCD4 project, I'm part of a working group on that, which is called the Magmatic Drivers of Eruption. This is actually taken from a webinar you can go and look at on the SC4D website. There's me talking in the webinar there with some flamingos in the background. And the topic that we're looking at is exactly what I've talked today. How do these transcrustal processes, how do the processes occurring deep within the crust underneath volcanoes initiate eruptions? And finally, if you're interested even more, there is an AGU session. It's going to be from 4 to 7. So actually, I think it's a pretty good time for Eastern Australia. There's also a poster session, which for me starts at 4 AM. That's just how AGU is. But if you're interested, please, and you're going to AGU remotely, please come along and join that. And with there, I'll end and take any questions.
All right, so I think Adam probably can't hear us. Is that right? So I just put this up here.
Thank you for that, the virtual hand claps. I will read the chat for questions.
Yeah. So, yeah, I think we are probably going to have to do it by typing in. There's one question's already there. Anybody else has them, just type them in and Adam can.
So Louis says, yes, do you have to worry about beam excitation? Yes, that's always true when you're measuring something that is thin. In this case, I didn't show it, but we can sort of back those iron concentrations up by doing some simple partitioning and calculating that they're in equilibrium with a reasonable mafic melt. But yeah, that's a very good point, Louis. And whenever you're dealing with thin things on the electron probe, I will say we've reproduced them with the laser, which doesn't have that same, you know, within the laser spot. Yes, you do have issues, and outside that, you don't. Another question. So how do I know that iron comes from the melt being mafic and not from a change in FO2 due to degassing? That's true. Iron is a slightly tricky element to work with in plagioclase because its partitioning is redox sensitive. It's also sensitive to the polymerization of the melt. But in this case, by looking at other elements like magnesium, which I think I showed, and then also a host of trace elements, strontium is another one, you know, you can build up a picture that it's not just iron itself that is changing, but it's also magnesium, which is not affected by that redox. So there's a question. I remain somewhat unclear as to the mechanism of magma injection eruption initiation. It's a good question. So if we talk about let's take about the simplest case where we have a magma that we inject with exactly the same composition. So there's no physical or chemical contrast. When we have those contrasts, like was shown by the classic work of Huppert and Sparks and Turner, all sorts of interesting thing happens because you change the temperature of the magmas at that interface, you change their densities because you exsolve volatiles, things like that. In the case of where you're ejecting exactly the same magma into itself, really your only option is that you have put so much stuff into that magma reservoir that you have just, you know, of roughly fixed volume or that cannot expand rapidly enough that you have increased overpressure that way. And that's certainly argued pretty consistent in the literature. You know, I guess the equivalent would be trying to blow up a balloon, but blowing it up so fast that you burst it, not because you reach the ultimate limit of the rubber, but because you reach the limit of how fast that rubber can expand. But I mean, this is my point. I actually don't really have a very good answer for your question because we don't quite know the physics and chemistry that even take a relatively simple process in that system I described, injecting exactly the same magma into each other, and how to translate that into an overpressure that eventually produces, you know, propagates a fracture to the surface, produces an eruption. So we have to kind of refocus on this and try and understand exactly what happens, because exactly what happens there is important to interpreting the monitoring signals. And then it also feeds back and it would refine the interpretation of the petrology that we see as well. And there'd be sort of iteration there, hopefully, where we would just end up understanding more with each iteration. Oh yeah. Yeah, I mean, silicic recharge, there is some evidence. So there's some papers, the Katmai eruption and Nova Rupta in 1912, which is one of, I think it's the biggest eruption of the 20th century, at least. Yeah, it is. It's bigger than Pinatubo. So it has been argued to result of intrusion of a rhyolitic dike into a rhyolitic magma chamber. The reason it's not in our compilation is one, it's subsequent work has reinterpreted that. And also that initial work didn't provide any timescale, and we've largely limited our compilation to studies that give us a timescale to work with because we're very interested in that. There's no real reason this couldn't happen, except that probably a lot of really silicic magmas are produced in those shallow magma chambers by sort of crystal liquid separation in place. Intermediate magmas are probably produced in the lower crust by melting of amphibolite, something like that. But the really silicic things like high silica rhyolites, perhaps one of the few places you can actually make those is in the shallow crust by, you know, separating crystals from liquid, and exactly how you do that is another interesting set of questions. But I wouldn't rule out that happening. I'm sure it's happened somewhere. It's just that the observational evidence, we just don't see much of it. That's a really good point. Because one thing that's very common is to see dissolution of minerals like quartz. I won't flip back in slides, but there are several slides, I didn't really point it out, where you see a nice rim on a euhedral crystal, but it's clearly that rim has crystallized on a magma that has undergone, on a crystal that's undergone some dissolution prior to that. And that's very common in quartz too. So I wouldn't rule that out. We'd have to think of some neat way to test it, whether it's possible to say do a anomaly anhydrous mineral study of that quartz and see if there is actually increase in hydrogen or something like that. But this is, sorry, I didn't read the question. It says in the volatile model rather than the magma injection, do you see systematic evidence of resorption of quartz? So the answer is yes, you do see a lot of resorption of quartz. During the build-up to eruption, as you might expect, as the volatile content rises slowly in stability fields across. That latter part, it sounds reasonable to me. I'd have to look at it in more detail, but certainly see a lot of evidence for resorption of quartz. Of course, I mean, the conventional interpretation is of that it's thermal. And when you're in a eutectic system, maybe you don't need to increase the temperature by, or actually you can't increase the temperature, but you increase the amount of melt present by adding something hotter that moves you further away from the eutectic point. I didn't explain that very well, but hopefully you got through.
So I'm just going to check if you can hear us at all, Adam. I think not. So let me at least thank Adam on behalf of everyone else, which will be evident in the recording, for giving this wonderful seminar this week. And
I can hear now too. I can hear now too.
Excellent.
Yeah.
Oh, well, should have fixed that before. Thank you very much, Adam.
Sorry about that.
Assisting through what was probably a bit complicated. Yeah, we'll say thank you very much. If you can hear, then I don't have to say what I was going to say, which is that we would have to sort of reorganize the early career researcher meet and greet. But if you're up for that, then thank you one more time.
Yeah.
I will cut off the recording at this point. There we go. Let me do that.